Hi, everyone. All right, I wanted to talk about kind of the two fun things that I worked on while I had the fellowship. And I wrote a talk for 25 minutes and then realized I had 15. So this is going to be a talk about ice sheets and one slide about octrees. But anyway, so I'm going to talk about accurate, scalable, efficient solvers for forward and inverse modeling on ice sheets. Standard talk outline, I'm just going to motivate. I'm going to talk a little bit about statistical and deterministic inversion in a very broad sense. My work on a day-to-day basis on developing discretizations and solvers for nonlinear Stokes equations for ice sheets, and then I'll show some results. Okay, so the motivation comes from the last IPCC report, the one that won the Nobel Prize with Al Gore in 2007. So pulling our favorite quote out of there, they can attribute a lot of the uncertainty in future climate variation to uncertainties in land ice models, so ice sheets and glaciers. And that uncertainty comes from the uncertainties in the parameters that people use to set up these models. So you can write down the equations, you can solve them, but the actual numbers that go in for the coefficients that change spatially really affect the problem. So here is the Antarctic ice sheet, and you see some small regions where it flows very quickly and otherwise large regions where it doesn't flow very quickly at all. And trying to understand the parameters that make up those differences is a very important climate problem. I've been working on tools that go from the climate data that we collect from scientists, discretization and simulation, to parameter estimation. So we want to get a good handle on these parameters to make accurate predictions. So looking at a very broad view of just a general parameter estimation problem, you can think of it in terms of probability distribution functions, where you've got your parameters, and you may have a distribution that describes some prior knowledge about it. And you have observations, which also probably have some kind of probability distribution, like noise or something like that. And you can think of your model as simply a map from the model parameters to the observations, a nonlinear map, and it may be probabilistic or it may be deterministic. So then to get the probability of a given set of parameters, given actual observations, you then apply Bayes' theorem to get at what a better description of the observations. So a very simple graphic, if you have a one observation and one parameter, you can sort of have the noise and your prior distribution, and then your model is this nonlinearity, and you multiply them together, and you get kind of a better description of what your parameter may actually be in reality, and hopefully your model description of then the distribution of the observations will still match the noise. Okay, so if you make some reasonable assumptions, like the fact that noise is Gaussian, and you can actually write down your prior distribution in terms of a covariance, you can then say that the posterior distribution will be distributed like the exponential of the sum of these two terms here. And we like that because if we try to define sort of the most likely point of the posterior distribution, that choice of the parameters is also the point that minimizes that term inside or the negative of that term inside the exponential. So this lets us get from very large intractable statistical inversion to deterministic inversion. So in my case, evaluating this misfit of the map from the data to the observations involves solving a nonlinear Stokes problem, so that's solving nonlinear PDEs. To then get the gradient of this, I then need to solve a related adjoint problem, so solving a linear problem, and that's just to get the gradient. And then if you get second derivative information of this functional here, that information, or the inverse of that information, is a good approximation of the covariance of your posterior distribution. So what that means is that I can not only give you sort of my best prediction for what the parameters are, I can give you some sense of the uncertainty in my number that I'm giving you. Am I confident in it? Am I not confident? Where am I most confident? Where am I least confident? That type of thing. So this is why we really like this way of coupling deterministic and statistical inversion techniques. Okay, so we're going to use the tools of PDE constrained optimization to do statistical and deterministic inversion. And for these values that we get out to make sense, we need to solve those nonlinear Stokes equations that were in the parameter to observable map. We want to do it accurately, efficiently, and robustly because we're going to have to do it many, 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 many times for many different possible parameters. So we want to do this not just for toy problems, but for sort of the full Antarctic ice sheet. So this is quite a large problem. So to motivate some of the physics behind this, here's if you go out onto an ice sheet, you can see regions where the ice flows very quickly, right next to regions where it's almost not flowing at all. So this is due to a nonlinear rheology of ice as a viscous creeping flow. So it's shear thinning. As you shear it, it gives more. So this makes it a nonlinear problem. We have variable viscosity. We have very complex boundary conditions. And in some cases, we need to solve this problem using a full three-dimensional representation, even though this thing stretches for tens of thousands of kilometers and is only 1 kilometer thick. So this really affects the equations and the way that they're discretized. Okay. This is hopefully the last slide of equations. So it's simply looking at the boundary value problem for these nonlinear Stokes. We've got momentum balance and incompressibility. And this parameter here that is the subject of our parameter inversion is the friction between the ice and the land underneath it. So is it almost stuck to the bedrock, or is it lubricated and sliding freely, this type of thing. So if you tried to write the effective viscosity of this Stokesian material, you would see that the velocity appears inside of that viscosity itself. That's the source of the nonlinearity, which means when we do something like linearize to solve a Newton step, the effective viscosity is now no longer just a scalar, it's a fourth order tensor coefficient. So this is a the Newton step ends up being a very general, highly heterogeneous linear Stokes problem. Okay, so how are we going to discretize this in the first place? Well, I said we want to do things accurately, so we're going to use higher order finite element method approaches. Here we have a stable pairing that you satisfy the incompressibility condition on each element. And important for computer architecture that as you go to higher order elements, you get more floating point operations per memory operation. So this is the way that computation really should be heading with the way that architecture is changing. As I said, we want to do efficient discretization, which means that when we need to get additional resolution, we don't want it everywhere. We're just going to use mesh refinement. So for instance, to capture the grounding line between floating and grounded ice, we start from the same coarse mesh and just refine in place. And the software that we use to do that is a package that was developed by a former researcher and that I've contributed a bit to called pforest. It's a parallel, highly scalable, adaptive mesh refinement library. I've managed to provide a bit of a speed up of the main mesh refinement loop by about a factor of 6 out to sort of the full Jaguar machine, the previous large-scale supercomputer at Oak Ridge. Okay, my one slide about octrees and octants. It's such a simple idea. You take a cube or a square and you divide it in half when you need more resolution. And you think it's really nice and predictable and, you know, it makes sense. But then when you go to 3D and you try to do things that you understood, you get a little bit more complicated. So I don't know if you can see this, but it's kind of nice to say, oh, well, you can build a fractal. But the ability to compute whether I'm inside of or outside of this Sierpinski staircase actually contributed a large deal to that speed up that I was able to get in this practical mesh refinement thing. So these types of problems are enjoyable in terms of very simple concepts yielding interesting solutions. Okay, back to what I really need to talk about. So the linear Stokes system is the heart of this. It's the heart of the nonlinear solve, which is the heart of the inverse problem. And we would like the convergence rate, our ability to solve this saddle point system with an elliptic block inside of it, independent of a whole bunch of things that can change in problems. We want to be able to refine the mesh, change the polynomial order. You know, we've got heterogeneous coefficients. This friction coefficient is going to go from almost 0 to almost infinite in some sense. We want to have nonconforming things that come out of our mesh refinement. And also to get to do an ice sheet, you really have to have all of your finite elements stretched out so that they're very thin. And this can be a big deal for three-dimensional approximations. So we're going to use a block-based preconditioner for that saddle point system. And it's going to be based on a multi-grid preconditioner for that one elliptic block inside the system. So I'm going to try not to be too technical about this. But suffice to say that if you use standard approaches to this, you can have a lot of pitfalls. So you'd like to see sort of good convergence for all sets of parameters. But if you choose the wrong mesh, you may have problems. If you choose the wrong finite element space, you may have problems. If you choose the wrong basis, you may have problems. If you choose the wrong quadrature, you may have problems. If you choose the wrong smoother within your multigrid, you may have problems. But finally, if you make all the right decisions, you can find something that you can stretch your elements out so that the aspect ratio is 100 to 1, and the finite element order can go from 3 to 9, fine like that. Okay, so here's a benchmark problem where you see this nice smooth variation in the friction at the bottom, but because of the nonlinearity in the rheology, you develop this one thin region of fast flow like I showed you in the picture. And so our nonlinear solver for this, the outer Newton iterations we can do at about 9 or 10, and the polynomial order of our approximation doesn't really affect things. And then if we use Picard, which is kind of like that near analytical gradient that you heard about in the previous talk, you would have to have 50 outer iterations and have much worse convergence. So now going to the full Antarctic ice sheet problem, where you have very small regions of fast flow like I talked about. The physics and geometry of this problem are a bit more challenging, so you have a few more iterations, but you still have sort of a good bound on the convergence rate even as you go to higher order elements. And then here's just one slide on showing that we can scale this problem out to 16,000 cores of the new TACC Stampede supercomputer. And finally, putting all of that inside of the inverse problem. So here's something that we were able to do just in the last few weeks of starting with a synthetic beta friction field, and then we run the forward situation to generate some observations and add some noise to obscure where they came from. And then we run our deterministic inverse problem, and we get back something that looks like this. So it smooths things out, but you still see some of the details and even some of the stream-like behavior as well. So this is sort of a promising first result. So I'd like to acknowledge all my coworkers in my research group, my advisor Omar Gattas, Georg Stadler, Noemi Petra, Johan Rudi, Hongyu Alisu, Karsten Berstede, for the main author of P-Forest, who's now at the University of Bonn, and of course the DOE CSGF program for giving me a chance to do the kind of research where I can put ice sheets and octrees in the title of the same talk. So with that, I'll be happy to take questions. Thank you.